Out there in the vastness of space, there are these objects that are so incredibly reliable, so precise. We actually use them as cosmic clocks. But what happens when one of those clocks starts to glitch? Let's dive into this little cosmic mystery. So first off, what are we even talking about? A pulsar. I want you to picture the collapsed core of a giant star, squeezed down into a ball maybe the size of a city, but it's spinning hundreds of times a second. Wild, right? And as it spins, it shoots out these intense beams of radio waves from its magnetic poles. If one of those beams happens to sweep past us here on Earth, our telescopes see a pulse, a little blip, over and over. It's just like a cosmic lighthouse guiding us through the universe. And the key word here is steady. The rotation of a pulsar is unbelievably stable. It's so stable, in fact, that scientists use them for these incredibly high-precision experiments, like hunting for the tiny ripples of gravitational waves. They are, without a doubt, the gold standard for keeping time on a cosmic scale. Which brings us right to the heart of our story. What happens when the most reliable thing you can possibly imagine suddenly starts acting weird? What does it mean when that perfect lighthouse beam starts to flicker? So let's meet our pulsar. It's called PSR B2217+47. It's about 8,000 light-years away from us over in the constellation Lacerta. And get this isn't just any pulsar. This is one of the 14 pulsars whose positions are etched onto the golden plaques of the Pioneer and Voyager spacecraft. Yeah, it's part of a map designed to help any intelligent life out there find its way back to us. And one of our most important cosmic signposts, well, it started sending a very, very strange signal. Okay, have a look at this. On the left, that's what a typical pulsar signal looks like, a nice, single, clean peak. Simple. But on the right, that's what astronomers using the LOFAR telescope started picking up from our pulsar. You see the main pulse? Sure. But then there's this weird second piece trailing just behind it, a phantom pulse. And here's the crazy part. This phantom pulse wasn't just sitting still. Over 6 years of watching it, astronomers saw it move. It showed up in 2012, and then it started drifting closer and closer to the main pulse. By 2015, it was almost right on top of it. This wasn't some simple glitch. This was something dynamic, something that was actively changing. The mystery was just getting deeper. Was the pulsar itself breaking down somehow? Was our cosmic clock broken? Or was something else going on? Seriously, what could possibly be causing this? Well, this kicked off what was basically a cosmic detective story. Scientists had to line up all the possible suspects and start checking the evidence to figure out what was behind this bizarre signal. So 3 main theories hit the table. First, maybe the pulsar itself was wobbling on its axis, kind of like a spinning top. Second, maybe the engine inside the pulsar that creates the radio waves was sputtering. Or third, maybe the pulsar was totally fine and something was just getting in the way between it and us. All right, let's look at suspect number 1, precession. This is the idea that the pulsar is physically wobbling. You know how a spinning top starts to wobble just before it falls over? Like that. A wobble like that would definitely change how we see its radio beam, and it could for sure change the shape of the pulse we detect. But here's the problem with that theory. The evidence just didn't add up. See, a wobble should mess with the entire pulse, the beginning, the middle, and the end. But this phantom signal, it only ever showed up after the main peak. The front of the pulse was totally normal. So, suspect number 1, ruled out. Okay, on to suspect number 2. Let's call this one a sputtering engine. This theory says the problem is coming from inside the pulsar itself, that the powerful magnetic field, the magnetosphere, that's actually generating the radio waves was having some kind of hiccup, creating an extra bit of signal. Now, this one seemed plausible until the astronomers looked at another piece of the puzzle. They noticed that the radio signal was also being delayed in a way that told them the density of the space between us and the pulsar was changing. It was like they were looking at the lighthouse through a patch of fog that was moving around. A problem inside the pulsar's engine just can't explain changes happening thousands of light years away from it. And that left only one possibility. So, if it wasn't the lighthouse itself, the answer had to be out there in the vast, seemingly empty void that the light was shining through. In their 2017 paper on this, the research team led by Michilli basically laid it out. They argued that the most likely cause was, and I quote, propagation effects in the ionized interstellar medium, or in plain English, it was something between the stars. It turns out the phantom pulse wasn't a phantom at all. It was an echo. The pulsar signal was actually taking two different routes to get to us here on Earth. One signal came straight to us, no problem. But another part of that same signal was hitting a huge invisible cloud of charged gas out there in space. It was getting bent just a little bit and then continuing on its way. But because that second path was just a little bit longer, it arrived just a fraction of a second after the direct signal, creating the illusion of a second trailing pulse.
So you might be wondering, how big was this cosmic cloud that was causing the echo? Well, based on their models, scientists figured it was about 30 astronomical units across. Now, 1 astronomical unit, or AU, is the distance from our Earth to the Sun. So, yeah, we are talking about something enormous. Let me put that into perspective for you. An invisible structure floating out in interstellar space, roughly the size of our entire solar system from the Sun all the way out to Neptune's orbit, just happened to drift right across our line of sight to this very specific pulsar. The odds are just mind-boggling.
And really, the evidence for this echo theory was just overwhelming. It all fit perfectly. The pulse was only trailing because, well, an echo has to arrive after the original sound, right? Same idea. The changes in that cosmic fog confirmed a dense object was moving past. And here's the clincher. When the main pulse was bright, the echo was bright. When the main pulse was dim, the echo was dim. It was a perfect reflection. It all just worked. Case closed. So yeah, a super cool cosmic mystery solved. But why does this one weird pulsar and its little echo matter so much? Well, this is where it gets really exciting, because the solution has some huge implications for astronomy. This discovery literally handed us a brand new tool. By looking for these echoes, we can now start to map the invisible clouds of gas and plasma that float between the stars. We can finally get a better handle on what that supposedly empty space is actually made of. It also tells us, hey, if we want to use pulsars as perfect clocks, we have to account for these cosmic fog banks. And it suggests that these solar system-sized structures, they might be all over the galaxy, just waiting for us to find them. Which really leaves us with one final amazing thought. The space between the stars, it isn't empty at all. It's filled with these immense invisible structures that we're only just now figuring out how to see. So if the light from one distant glitching pulsar can reveal a hidden cloud the size of our own solar system, what else is out there, hiding in the dark?